This is a tutorial on section B of electromagnetism, and the only reason why we're doing a detailed tutorial specific to just one section in one chapter in physics is because we know how tough it is as a student to learn this at first go, and also how tough it is to teach it and get everyone to understand it. And that's when you have just a blackboard and a piece of chalk with you, or you're reading from a book, because this chapter involves a lot of imagining, and you need to imagine stuff that is 3D really, and it's tough to do that when you're just reading from a book. And this is actually one of the reasons why we're doing this whole thing in the first place, trying to make use of animations, videos, graphics like these over here we have. So we're going to start off, and hopefully you're going to get this at the first go. If you don't, you can watch the video again or contact us or whatever. I'm going to start off with Lorentz Force because this forms the basis of this section. What he basically said, he being Henrik Lorentz, he's a Dutch physicist. I think he won the Nobel Prize as well. He researched a lot in this area, electromagnetism, and I think he is also very closely associated with Einstein. So now he noted these observations. The main part, the main theory of his was that when you place a current carrying conductor in a magnetic field, it experiences a force. I'll come to the more specific parts of that statement. So now I've just drawn boxes, 5 cases. Now I'm going to go through each case. In each case, we have a magnet. We're taking a horseshoe magnet here because it's simpler to understand. And we're taking a conductor. I'm going to denote the conductor in, say, blue. Conductor is in blue. Just write CON. And say our magnetic field lines. I think you know what they are. You would have done this in section A. It's all the lines going from north to south in the magnets. So I'm just writing north south here. And let's also denote the force by another color, say a yellow. This is the force. I'm writing F. And this force, mind you, is called Lorentz Force. It's the heading right now. So I'm going to start with case 1 now. The magnet is here. This is your horseshoe magnet. Okay, this is north, this is south. So the first thing we can say is that the magnetic field lines, let's draw them straight here, are going like this because they always go from north to south. Now, say you place a conductor, just a wire, and note that I said conductor, not current carrying conductor. Say your conductor is in blue, right? So just place it like this and don't pass any current through it. Let's denote current carrying conductor by orange. So there's a difference here. This is just a conductor. The difference is that this is a wire on its own. This is a wire that's carrying any current, whether it's small or big, doesn't matter, it's carrying current. So in this case, case 1, it's just a conductor, just one wire placed there, no current, and so the force that it will experience will be nothing. I don't know why I'm choosing yellow, but it'll be nothing. There'll be no force acting here. So no current, no force. That's a basic case over here. Now, let's just do the second case. Now you turn on the current. So again, north and south over here. So your field lines will remain the same. I should probably draw the arrows over here depicting north to south. Okay. Now, in this case, we're not only placing a conductor, we're placing a current carrying conductor, and we're placing it like this, horizontally. Now, what Lorentz observed was that that conductor experiences a force that is perpendicular to both the direction of the current as well as the direction of the field lines. Now, perpendicular, I think you know, it means 90 degrees. Now, just imagine that the orange is your x-axis. This is why I've drawn this diagram here. Just imagine that your x-axis is the line in orange, and the one in green is your y-axis. So you can agree that they're perpendicular so far. Now the force that the conductor will experience will be perpendicular to both of them. Now the way to imagine this is you have something called z-axis as well. I don't know if you've done it so far in math, but you will be doing it next for sure. So imagine you have a piece of paper. Draw your x-axis horizontally, draw your y-axis vertically, and say you stick a stick or a pencil through it. That will be your z-axis. So if you look at it, z-axis is just cutting through the paper and going from front to back. That's your z-axis. Now if you look at the z-axis, it's perpendicular to the x-axis. And I know this diagram you might not be able to visualize this. Just look at it as a 3D diagram. Imagine the z is going into the screen. So z is perpendicular to x, it's making a 90-degree angle, and it's also perpendicular to the y. So in both cases, it is perpendicular to both the current as well as the magnetic field lines. So the force that it will experience in this case, in case 2, will actually go inside or outside. That depends on the direction of your current. We'll come to that as well. But just know for now that it will either be like inside over here, inside the screen, or it'll be outside the screen, right? And that depends on whether you're drawing an arrow like this or an arrow like this. We'll come to that when we do the left hand rule. Now in the third case, what we're doing is reversing the direction of the current. So let's just take this diagram again. I need to draw that in red. Okay, this is your magnet, north and south. So field lines are the same still. Arrows like this. Okay, so imagine that in case 2, your current was going this way. Now the force, now you need to look at this left hand rule graphic that is here. Just put your left hand out like this, and just put it out like it's shown over here, and point, try and match the magnetic field and the direction of current as I've drawn in case 2. So what you'll be doing is your middle finger is the direction of current, and the current is going like at the x-axis horizontally. So keep your finger like that. Now your magnetic field is going vertically down. So if you bring your index finger down fully, you'll see that your thumb will automatically point inwards. It's going to point inwards. So we can say that if your current is going towards the right in case 2, your force will be inwards. Now if I take case 3, now the current is going the other way, towards the left. Now if you do the left hand rule again, magnetic field remains the same, so your index finger is still pointing down, but your direction of current is now left. So just twist your hand around, and now what you get is your thumb is pointing towards you, outside the screen basically. So your force will be like this. Your whole wire will be pushed towards you, while in case 2, it's going to be pushed inside the screen. I should rub this other arrow out because it doesn't hold true anymore. Okay, now this is it. This is the main part, but there are another 2 conditions. The first one is that if you reverse the direction of the magnetic field, same, a horseshoe magnet is not going to change. It still remains. Sorry, yeah. But what changes is the north and the south. So your north is below while your south is above. We said that we're changing the direction of the magnetic field. Okay. So magnetic field was in green. So now it's going up, and your arrow will come like this. Now, if you take your conductor again, current carrying conductor, that is, place it like case 2. It's on the right. Now extend your left hand. Your magnetic field is now going upwards. So point your index finger, your forefinger, that is upwards. This one, by the way, this is going up. Your direction of current is going rightwards. So what you see is that your thumb will be pointing towards you. So the force will be out. So if you can see, compare case 2 and case 4. The only thing that we changed was the direction of the magnetic field lines, and what changed at the same time was the direction of the force. Instead of going inside the screen, it's coming out of the screen. Now, there's another case, same thing actually. I'm going to make it in this case only. Oh, why not have space? I might as well make another one. If you reverse the direction of the current, the same thing is going to happen. So let's take case 2 again. This is north, this is south. That's where the field lines, they'll be going down again. We're back to going down, and we're saying reversing the direction of the current. That means instead of right over here, this is the case we're talking about, we're going left now. So we take our orange conductor, current carrying conductor, it's going left. Now apply the left hand thumb rule. Your magnetic field is going down, which is the same case too, and now your direction of current is leftwards. So you can see your thumb will be again pointing towards you, and also at the same time just twist your hand around 180 degrees, and you see that if your middle finger points towards the right instead of the left, you can see that your thumb will also change direction and go inside instead of outside. So it's clear from these 5 cases that if you reverse the direction of magnetic field lines, the direction of force will also be reversed. If you reverse the direction of current, the same thing will happen. And there's another case. It's not really a case, it's just a rule. I'm just going to do a small thing over here. So say this is your magnet, north, south. Field lines will go like this downwards. Sorry, it's a bit messy, but I think you get the point. And say you have a current conductor and it's placed exactly parallel like this, downwards. That means that it's not cutting any of the green lines, and that cutting of the green lines is called flux, magnetic flux. So since there's no magnetic flux, this whole force will be out of the picture totally. So all you need to remember is that if your conductor, say it's like this, and your field lines are also like this, you can see that it's not going to cut any of those green lines. However, if you even have it like this, it will cut, but the effect will not be that great. So this is the case that you'll be taking for all of your problems involving Lorentz force. So I'm out of time here. I think I'm reaching 15 minutes, which is a lot. So I'm going to continue it from here, go into DC motor in the next tutorial.